Okay, let's continue with the postulates. So in the first postulate, we have seen that the macro state of a composite system can be described by specifying the internal energy U, the volume V, and the number of particles N. And the second postulate, we have seen that there exists a function of these extrinsic parameters named the entropy S, which is defined for all states of the system. And if the internal constraints of the system is relaxed, then these variables, the extrinsic parameters U, V, N, will be achieving such a state which will maximize the value of the entropy of the composite system. Okay, or we have seen that S equal to S of U, V, N is a fundamental equation of the equation of state for the thermodynamic system. Now we go to the third postulate of equilibrium thermodynamics, which says about the additive nature of entropy of the system. So that's the only thing, or the extensive nature of the entropy of the system. So let's read the postulate and then try to understand it. So the postulate says the entropy of a composite system. So when I say a composite system, see that you have the imaginary diagram in your mind, a composite system which is made up of maybe 2 or 3 subsystems, say 1, 2, and 3. So the entropy of a composite system is additive over each one of the individual components. So the first component is here. This is a pure fluid, subsystem 1, subsystem 2, and subsystem 3. So what is the total entropy of this composite system? Then the postulate says that the total entropy of the composite system, S, it will be equal to, S will be equal to simply S1 plus, that is entropy of subsystem 1 plus what? Entropy of subsystem 2 plus entropy of the subsystem 3. Okay, or it also says that the entropy is a continuous, differentiable, and monotonically increasing function of energy. I will explain it, okay, on the way, right? So it's a mathematical statement. See, so the first part of the third postulate says that entropy is additive. What is meant by entropy is additive? It means that entropy is an extensive parameter. Hope you remember our definition of intensive and extensive parameters in thermodynamics. Okay, so we said in the other way. What we say? We said that if a system is divided into parts, if some properties of the system is also getting divided, then those properties are what is known as extensive. And those properties which remain same for even for the parts, then we call them as intensive. So here you can see it's putting in the reverse sense. നേരെ തിരിച്ചു പറയുന്നേ ഉള്ളൂ. ഒരു കോമ്പോസിറ്റ് സിസ്റ്റത്തിൻ്റെ ആകെ എൻട്രോപ്പി എന്ന് പറയുന്നത് ആ കോമ്പോസിറ്റ് സിസ്റ്റത്തിൻ്റെ പാർട്ടുകളുടെ എൻട്രോപ്പിയുടെ സമ്മാണ് എങ്കിൽ then we say that that entropy is behaving like an extensive parameter. So നിങ്ങൾ ഇങ്ങനെ ഓർത്താൽ മതിയാവും. Third postulate says about the extensive nature of entropy. Okay, ഇത് കുറച്ചുകൂടി ഡീറ്റെയിൽഡ് ആയിട്ട് എഴുതുവാണെങ്കിൽ എസ് എന്നുള്ളത് എസ് എ ഫംഗ്ഷൻ ഓഫ് നമ്മൾ നേരത്തെ കണ്ടു U1 V1 N1 U2 V2 N2 കോമ്പോസിറ്റ് സിസ്റ്റത്തിൻ്റെ എൻട്രോപ്പിയാണ് ആൻഡ് സോ ഓൺ. ഓക്കെ, ആൻഡ് സോ ദാറ്റ് വിൽ ബി ഈക്വൽ ടു if you have only 2 subsystems, then what then I can write it is simply S1, which is a function of U1 V1 En1 plus what? S2, which is a function of U2 V2 and N2. Okay, so if you have got only 2 subsystems, this is the meaning of the first sentence of third postulate. Okay, now we have to also explain that the entropy is a continuous, differentiable, and monotonically increasing function of energy. Okay, I think continuity and differentiability are the properties of entropy that can be understood. What is the meaning of monotonically increasing function of energy? So it just means like this. Suppose that you are drawing a graph. Okay, you draw a graph between you say that energy, internal energy U here, and entropy here. So this statement says that okay, the entropy will be increasing. Entropy will be increasing steadily, as you increase the internal energy of the system, the entropy of the system also will be increased. So the graph between entropy and this one will be showing an increase. Or we can say that if you take the slope of this particular line, you take the slope of this line, okay, so what is the slope of the line showing? I can say that it is showing either, I can say slope is dy by dx for any graph, so it is ds by du, or I can write it as a partial derivative, because s is a function of several variables. S is a function of u, v and n. So instead of writing ds by du, it's better that you write as dou s by dou u. Is not, because s is a multivariable function. Okay, so I prefer to write in terms of partial derivatives. Dou s by dou u okay, is greater than 0. What is dou s by dou u meaning? Dou s by dou u represents what? The slope of SU graph. So slope is always positive. So the entropy energy graph will be always having a positive slope. That's the meaning of the second part. The entropy is a continuous and differentiable. Only if it is continuous and differentiable, we can just have a mathematical manipulation of that function. Okay, you can take derivatives only if it is continuous and it is differentiable. And not only that, it's a monotonically increasing function of energy. Means ds by du is defined. That is, or dou s by dou u is defined. That's one thing. Means s is differentiable with respect to u, and the derivative of s with respect to u is always positive. Okay, so that's the meaning of this second. So s is a monotonically means it's never decreasing. Okay, it's always increasing. S is a monotonically increasing function of u. When u increases, s is not going to decrease. S is always going to increase. Okay, so that is the thing. Now see, just one thing for your attention. We have seen from the second postulate that you can express the entropy S as a function of U, V and En, the intensity properties of the system. And I told you that this is a fundamental equation of the thermodynamic system. And what you can do, you can invert this equation if you want. Okay, so you are suppose that you are writing S equal to a function of u, v, n. Then what you can do, from that you can isolate u. U in a matrix. U in a matrix. Either equation like you are writing see A is equal to say that B by C you are writing, right? Okay, so you are writing A in terms of B and C. Then you can write B in terms of A and C also. Like, so you can write, or you can write B is equal to A into C. Same manner, S equal to S of UVN. You can write the internal energy U as a function of S, V, N also. You can write S as U as a function of what? S, V, N also. Or okay. So you can see that is what okay. ഇങ്ങനെ തിരിച്ചു വേണമെങ്കിൽ നമുക്ക് എഴുതാൻ പറ്റും. ഇങ്ങനെ എഴുതിയാൽ പോലും എന്താണ് ഇതും ഒരു ഫണ്ടമെന്റൽ ഇക്വേഷൻ ഓഫ് സ്റ്റേറ്റ് ആയിട്ടാണ് വിളിക്കുക. Okay, so either you can write the fundamental equation of the state as S as a function of UVN, or you can invert this equation to represent U as a function of SVN. ഈ രണ്ട് രീതിയിലും ഒരു ഇക്വേഷൻ നമുക്ക് ഒരു സിസ്റ്റത്തെ പറ്റി എഴുതാൻ പറ്റിയാൽ നമുക്ക് സിസ്റ്റത്തിന്റെ തെർമോഡൈനാമിക് പ്രോപ്പർട്ടീസ് ഒക്കെ ഇതിൽ നിന്ന് തുടങ്ങി മറ്റു പ്രോപ്പർട്ടീസ് കണ്ടെത്താൻ പറ്റും. അതുകൊണ്ട് ഇത് രണ്ടും എന്താണ് see both of these are considered to be a fundamental equation of state. So that's what is given. We can invert the functional form of S to write U as a function of SVN, which is also a fundamental equation, like S is a function of what? UVN. നമ്മൾ ഇതിനുള്ള ജസ്റ്റിഫിക്കേഷൻസ് ഒക്കെ സ്റ്റാറ്റിസ്റ്റിക്കൽ മെക്കാനിക്സിൻ്റെ മൊഡ്യൂൾ നമ്പർ 2 തൊട്ട് നമ്മൾ ചെയ്യുമ്പോൾ ഐ വിൽ ബി ഗിവിംഗ് യു ജസ്റ്റിഫിക്കേഷൻ ഫോർ ഈച്ച് ഓഫ് ദ പോസ്റ്റ്ലേറ്റ് ദാറ്റ് വി ആർ ജസ്റ്റ് ഡിസ്കസിങ് ഹിയർ. ഇനി ഓക്കെ, ഇവിടെ ഒരു ബിഫോർ വി മൂവ് ഓൺ ടു ദ തേർഡ് പോസ്റ്റ്ലേറ്റ്, നമ്മളിവിടെ കണ്ട ഒരു ക്വാണ്ടിറ്റി ഓർത്തോണേ, ഡോ എസ് ബൈ ഡോ യു. എന്താണ് ഈ ഡോ എസ് ബൈ ഡോ യുവിൻ്റെ റെലവൻസ്, ഫിസിക്കൽ റെലവൻസ് എന്നൊക്കെ നമ്മൾ മുൻപോട്ടേക്ക് പോകുമ്പോൾ കാണും. ഇനി ബിഫോർ വി മൂവ് ഓൺ ടു ദ തേർഡ് പോസ്റ്റ്ലേറ്റ്, let me introduce a concept of what is meant by homogeneous functions. Okay, homogeneous functions എന്നുള്ള ഒരു യൂസേജ് നമ്മൾ പറയും എക്സ്റ്റൻസീവ് വേരിയബിൾസിനെ എക്സ്പ്ലെയിൻ ചെയ്യാൻ വേണ്ടിയിട്ട് നമ്മളൊരു മാത്തമാറ്റിക്കൽ ലാംഗ്വേജ് മുൻപ് ഉപയോഗിച്ചിരുന്നു. എക്സ്റ്റൻസീവ് വേരിയബിൾസ്, എക്സ്റ്റൻസീവ് പാരാമീറ്റേഴ്സ് ആർ ഓൾവേസ് ഹോമോജീനിയസ് ഫങ്ഷൻസ് ഓഫ് ഫസ്റ്റ് ഡിഗ്രി എന്നാണ് നമ്മൾ പറയുക. Okay, so now before we move on to the third of next postulate, final postulate, let me explain what's my homogeneous functions. Okay, what is my homogeneous functions? You consider a function. Okay, we are considering a mathematical function, for example, a function of single variable, say f of x. Okay, so x is the variable and f of x is a function. Now what I'm doing, if I'm replacing x by say some lambda x, where lambda is some number like 1, 2, 3 like that, or even it can be 0. Okay, then if you replace x in the function by lambda x, then f of lambda x, so I'm replacing x by lambda x, so I have to write f of lambda x, so x is replaced by lambda x. If f of lambda x can be written as lambda times f of x, if f of lambda x can be written as what? Lambda times f of x, then f of x, this f of x is said to be a homogeneous function, homogeneous function in x. It's a homogeneous function in x of degree 1. Now, okay, see, it can be put in some general form, right? That is, or I'm general. So I define what is my homogeneous function of degree 1. That is, if x is replaced by lambda x, then f of lambda x is becoming lambda raised to n into f of x, then f of x is said to be, if this is the case, is said to be, what you can complete it, a homogeneous function. It is said to be a homogeneous function in x, x-ilulla homogeneous function, but of degree, രണ്ട് കാര്യങ്ങൾ പ്രധാനപ്പെട്ടതാണ്, of degree n. So you can see here whatever comes as here, the degree of this lambda, then that is the degree of that function. Okay, now so far we took a function of single variable. Let me take as a multivariable function. Okay, so for a multivariable function, say for a multivariable function, because in thermodynamics and statmech we usually come across a large number of multivariable functions. What is a multivariable function? A function which depends upon a number of variables. For example, u equal to u of svn, or s equal to s of uvn. So s depends on not only on u, it depends on v and n as well. So it's a multivariable function. For a multivariable function, okay, say f of some function x1, x2, x3, etc. It can be xyz. Okay, I'm calling it as x1, x2, x3. Okay, it is said to be a homogeneous function of degree n in variables x1, x2, x3, etc. if for any value of lambda, f of lambda x1, means I am multiplying x1 with lambda, I am multiplying x2 also with lambda x2, lambda x3, etc. If this is equal to lambda raised to n into the original function f of x1, x2, x3, etc. Then we will say that this function is a homogeneous function of degree n in variables x1, x2, x3, etc. So that is a general. So I will give you an example. I think an example will make the story clear. Okay, so I'm taking an example. you consider a function of two variables, say for example x and y. You take an example, okay, f of xy. So it's a function of two variables, okay, x1, x2, or x and y. Let me, you can take any function. So let's take some function like some x by y, or something like x by, say, x square plus y square. Say I'm taking a simple function x by x square plus y square. Now what I'm doing, if x equal to say lambda x, lambda can be some number 1 2 3 4 like that, okay. If x equal to lambda x, and also what I have to do, same thing I have to change with y. So y is equal to lambda y. So I'm changing x with the lambda x and y with the lambda y. Then therefore what will be f of lambda x lambda y. So this is the question. What will be the value of the function when lambda x lambda y? So what? Let's find it out. So x is replaced by lambda x. Now x in the denominator is replaced by lambda x. So I have to write lambda x the square plus y in the denominator is also changed by lambda y. So I'm writing lambda y the whole square. So what will be this one? It will be equal to lambda x divided by, the denominator will be lambda square x square plus lambda square y square. So I can take lambda square outside and I can write lambda square into x square plus what? Y square. Am I right? So what will happen here? So this lambda will be getting cancelled out. One of the lambda will be getting cancelled. So what I will getting is what? Lambda is there in the denominator. I'm writing as raised to -1. Lambda raised to -1 into x divided by, again, what is that? X square plus y square. And what is this x by x square plus y square? And that's nothing but what is what? Lambda raised to -1 f of xy itself, our original function. Okay. So can you see that now f of lambda x lambda y is equal to lambda raised to -1 of f of xy. So what do we call? So this function is said to be a homogeneous function of degree -1. So this is a function is a homogeneous function of degree what? Degree -1. So degree can be even -1, -1, -2, whatever it is. Okay. Now, why did I introduce the concept of homogeneous functions? You can understand that. Okay, here you have seen S, is not? S was written as a function of S is a function of UVen. Now the question is that if U is made to U, V is made to V, and N is made to N. What's the meaning? The internal energy of the system is doubled, the volume of the system is doubled, and the number of particles of the system is doubled. What will happen to the entropy of the composite system? That's the question. So what will happen is that then, therefore, what will happen? You can see that it will be equal to see S of 2U, 2V, 2N. You will be see that it will be equal to simply 2 times S of UVN. S of UVN. 2 times means 2 raised to 1. And what is this 2 here? What is the status of 2 here compared to our theory? Lambda is equal to 2. Is not? Here it is multiplied twice, lambda x, lambda y. So here I am multiplying UVN by 2. So lambda equal to 2 in our example. So S of 2U, 2V, 2N will be equal to 2 into S of UVN. What's the meaning? It means that like if you double the volume, double the number of particles, double the internal energy, it means what? The entropy is also getting doubled. Or can't you think in the reverse? If you half the number of particles, half the number of volume, half the internal energy, what will happen to the entropy of the system? The entropy also will be getting what? Halved. Is not the property of an extensive variable that if the system is divided, if the number of particles is divided, if the volume is divided, okay, then what will happen to that property? The property also will be getting divided. So it means that entropy is an extensive variable. So in general we can say that, can't you see that what's the degree of this homogeneous function? We can say that entropy is a homogeneous function in U, V and N of degree 1. So S is a homogeneous function of U, V and N of degree 1. Or we can say that every extensive variable, this is a generalization, every extensive variable will be a homogeneous function of degree 1. Extensive parameter, this is general mathematical language, every extensive parameter is a homogeneous function of degree 1. It's a homogeneous function of degree 1. So what about an intensive parameter then? What will be the degree of an intensive parameter? We can see that if the property is an intensive parameter, then instead of here, so if you double it, lambda equal to, let me make lambda still equal to 2. So instead of 1 coming over here, okay, it will be 2 raised to 0. 2 raised to 0. The degree will be 0. Why? 2 raised to 0 means 1. So means even if you pressure, for example, okay, you double all the values, okay, you double all the values, then what will happen? For example, pressure, okay, so you double the volume, you double the number of particles, etc. Then also what will happen? The pressure will be remaining what? The same. It means that the intensive variables are homogeneous functions of degree 0, means it won't be getting affected, whereas extensive variables will be homogeneous functions of degree 1. That gives you another definition for what are intensive and extensive parameters. So if you are asked to distinguish between intensive and extensive parameter, a mathematical difference can be stated like this: or all extensive parameters are homogeneous functions of degree 1, whereas all intensive parameters are homogeneous functions of degree 0. Okay, so that is the meaning of intensive and extensive parameter. Now we are in a state to go to the fourth postulate of equilibrium thermodynamics. So what's the fourth postulate? Let's see. It says that the entropy vanishes in a state when dou u by dou s is equal to 0. Entropy vanishes in a state when dou u by dou s equal to 0. Do you remember this parameter dou u by dou s ever before? Have you seen this parameter dou u by dou s? You'll understand that we have seen dou u by dou s in the third postulate. Let me go back. Dou u by dou s. Can't you see that dou s by dou u here you have seen? Okay, no, dou s by dou u. So the inverse of dou s by dou u is what is dou u by dou s. Okay, so let's see what is meant by dou u by dou s. Right? Dou u by dou s. So let me go to that one. Right? So here they say dou u by, the entropy vanishes in a state when dou u by dou s, keeping v and n constant. You know what's the meaning of this one, because you know that you can either write u can be written as a function of svn. I told you both the ways it can be written. Or you can write s as a function of what? Invert. UVN. Both the ways of writing are correct. So if you're writing u as a function of SVN, then you can define dou u with respect to the variable s, dou u by dou s. When you take this partial derivative, you are supposed to keep the other two variables as what? Fixed. So that is why v and n are taken to be constant here. Okay, partial derivative. And the fourth postulate says that entropy vanishes when this physical quantity, this partial derivative is equal to 0. So means this partial derivative has got some significance in thermodynamics. Let's understand what's the meaning of this partial derivative. So to understand the meaning of this partial derivative, let me take you to the differential form of the first law of thermodynamics. What is the differential form of the first law of thermodynamics? We have seen that for an open system, du is equal to T ds, okay, minus P dV plus mu dn. Hope you remember still this particular differential form of the first law of thermodynamics for an open system, because I am including mu dn also. Now from this, can't you find out this quantity? Can't you find out this partial derivative? So how do you do that? I have to take dou u by dou s. So means keeping v and n constant. Keeping v and n constant means if you keep v and n constant, when you keep v constant, dv will be equal to 0. When you keep n constant, what? Dn will be equal to 0. So what you are left with, these two terms are gone, that is 0. So what you are left with? You are left with du and tds. So what is then? Can you write from this one? Du, dou u by dou s. Can you see it? What is dou u by dou s turning out to be? dou u by dou s, keeping v and n constant, what is remaining here? So I'm taking ds to this side, so it is T. And you know what is this quantity then? This quantity is nothing but the thermodynamic temperature or absolute temperature. Okay, so this is the temperature, the definition of temperature, thermodynamic definition of temperature. So so what is the fourth postulate just saying? The fourth postulate just says that, okay, it establishes the already, okay, non-fact in another form. The entropy vanishes in a state when the temperature, absolute temperature, vanishes. Or it simply says that when T equal to 0, 0 means it's absolute temperature, so it's 0 means 0 Kelvin, then entropy of any system also would have achieved its what? 0 value, S equal to 0. And aren't you familiar with this particular fact? This fact only what you have named as the third law of thermodynamics. So this is nothing but the third law of thermodynamics. You know, the third law of thermodynamics is stated in multiple ways. പല രീതിയിൽ third law of thermodynamics പറയാറുണ്ട്. Okay, and this is what is known as the Nernst Law. അങ്ങനെയാണ് പറയാറുള്ളത്. Nernst form of third law of thermodynamics. Heat capacities of crystals-ന്റെ കേസിലും പറയാറുണ്ട്. CVCP-യുടെ ടേംസിലും third law പറയാറുണ്ട്. But this is known as Nernst Law. Nernst Law എന്ന് പറയുന്നത്. Nernst Law is one of the forms of what third law of thermodynamics. It just says that at absolute zero of the temperature, the entropy vanishes. Okay, entropy, that is the fourth postulate says that entropy vanishes at absolute zero of temperature. That is the fourth postulate. Okay, so that's all about the postulates of equilibrium thermodynamics. Let me, before we end up the session, let me recap what all things we have learned in the postulate. So we began by defining what is meant by a simple system. You know, a simple system is composed of a pure fluid which is which is a single component, free from all external fields, okay, which is homogeneous, which is isotropic. Okay, so a combination of simple systems is what is known as a composite system. And the postulates of equilibrium thermodynamics answers the fundamental problem of equilibrium thermodynamics, which is finding out answer to the question that what will happen if the internal constraints of a composite system are relaxed one by one. Means the boundaries are relaxed. If adiabatic is made conducting, if impermeable is made permeable, if immovable boundary is made a movable boundary, then how the system will be trying to again achieve equilibrium, how the system will re-equilibrate. And the answer to the question is given by the postulates. And the first postulate just defines the existence, okay, of macro state, or it defines how a system's macro state can be explained. So it says that the macro state of the system can be expressed in terms of U, V and N, three extensive parameters. Second postulate defines the existence of what is known as what? Entropy. And it says that the entropy of a system will be achieving a maximum when the system achieves what? Equilibrium. Third postulate is also talking about entropy, but it talks about the additive nature of the entropy, or the extensive nature of the entropy. It says that for a composite system, the entropy of the entropy will be equal to the sum of its parts, S equal to S1 plus S2 plus S3. Or entropy is established as a homogeneous function of degree 1. And the fourth postulate says that the entropy of the system vanishes in a state when its absolute temperature is what? 0. Okay, so these are the four postulates, and we'll be using these postulates in the discussion of the fundamental principles of statistical mechanics. So keep in mind. Okay, a word of caution for you, even though the postulates have been explained in detail, see that you try to, by repeated reading or repeated usage, you try to read the try to memorize the statement for our purposes. Okay, so the wordings are something important so that we do not miss out the meaning in between. Okay, so read repeatedly, use it repeatedly until and understand the concept from the discussion that we have done. Okay, so that's about the postulates of equilibrium thermodynamics. I hope that in the next session we'll start with the basic right, what you call the Gibbs-Duhem relationships and the intensive parameters of thermodynamics in a better way. Okay, thank you.